PointPatchMix, point cloud mixing with patch scoring. The point cloud classification task is very important for 3D scene understanding. Its goal is to identify and differentiate various objects or entities represented within the point cloud by learning spatial information and features within point cloud data. Deep neural networks have made remarkable progress in this area in recent years, giving birth to classic architectures such as PointNet and PointNet, as well as the advanced model Point-MAE based on the transformer architecture. The precise classification of point clouds has emerged as a pivotal and intricate research focus in the field of computer vision, boasting extensive applications in real-world scenarios such as virtual reality, augmented reality, and autonomous navigation. However, the scarcity of point cloud training data inherently exposes DNNs to overfitting risk, attributed to their inclination to model approximation based on the given data distribution. To alleviate this challenge, many works have put efforts into point cloud data augmentation techniques which serve to enrich the variety within the training data, thereby enhancing the generalizability of point cloud classifiers. Notably, among them, mixing-based augmentation has shown great potential for point clouds. In this paradigm, mixed point clouds are endowed with labels derived from their original counterparts. For instance, PointMixup defines data augmentation between point clouds as a shortest path linear interpolation and generates new samples by optimally assigning a path function. Similarly, PointCutMix determines optimal correspondences between two point clouds and create fresh training instances through point replacement. However, there still remain some limitations. Firstly, the above two methods manifest limitations in their generation of mixed point clouds, operating predominantly at either the block or point levels. Although point-level mixing can increase the diversity of training samples, it may not adequately preserve the local characteristics of the point cloud. While block-level mixing may limit the diversity of the generated point clouds when retaining local features. Striking a balance between diversity and accuracy can therefore be challenging. Furthermore, they generate targets for mixed point clouds through a simple linear combination based on the point cloud sample ratio. However, it may not be optimal for many scenarios where the importance of each patch in the point cloud may significantly differ. Therefore, it is imperative to develop an augmentation method at the patch level that generates content-based targets. To overcome these challenges, we propose PointPatchMix, a novel point cloud mixing method that operates at the patch level and integrates a patch scoring module. As shown in the figure, the original point clouds are divided into multiple patches, subsequently undergoing mask token processing and mixing. Then, we generate significant scores for each patch using a pre-trained teacher network, which considers the value of the information contained in each patch. Finally, the mixed point cloud consists of patches selected by mask tokens and the new ground truth is generated. So, how does PointPatchMix work? It has two core parts, namely point patch scoring and point patch mixing. First, the point patch scoring module can generate content-based targets. Our intuition is that not all patches in point clouds contribute equally to classification accuracy. Consequently, a crucial aspect of our approach is determining each patch's significance score. In a typical self-attention layer of a transformer, the attention matrix A can be obtained by queries and keys, both of which are derived from the input token. In our module, the first token is the classification token, so, 1, signifies the relevance of patch token J to the classification token. In this way we can easily get the significance score of each patch. In the point patch mix, we use the Earth mover's distance function to determine the optimal assignment of the point cloud at the patch level. Subsequently, we generate a patch-level random mask empty based on the mixing ratio. Finally, a new mixed training sample can be constructed with the significance score from the pre-trained teacher model. We conduct extensive experiments on both synthetic and real-world datasets in point cloud shape classification to evaluate the effectiveness of PointPatchMix, i.e., ModelNet40 and ScanObjectNN. Meanwhile, in order to ensure that PointPatchMix is a general data augmentation method, we select multiple popular architectures in the current point cloud field to evaluate its availability and effectiveness. In addition to the architectures PointNet and PointNet mentioned above, we also adopt the latest advanced models such as PointMLP and PointGPT. We mainly utilize Point-MAE, a robust classification model, as our baseline. Our model achieves 86.3 accuracy on ScanObjectNN and 94.1 accuracy on ModelNet40, which outperforms previous methods by a notable margin. PointPatchMix also demonstrates remarkable generalization across diverse architectures, enabling the state-of-the-art architecture, PointGPT, to achieve a remarkable accuracy rate of 88.3 on ScanObjectNN. To evaluate the contribution of each component in PointPatchMix, we conduct ablation studies on ModelNet40. We mainly use the transformer proposed in Point-MAE without pre-training as our baseline model for evaluation, which archives 91.4 on ModelNet40. We study the impact of different choices on classification performance from 4 parts: mixing level, target generation, patch assignment, and beta value respectively. The configuration of patch level, score combination, center points, 1.5 was finally determined as the best configuration, and they further verified the effectiveness of point patch scoring in PointPatchMix. In the qualitative analysis, we firstly present a visualization of the patch scores in the upper right plot. Content-rich patches are closer to red, while unimportant patches are closer to blue. As we can directly observe, edge patches, e.g., the wing of airplane, the head of guitar, and some key local patches, e.g., the wick of lamp, the leaf of plant, often contain rich semantics. We also present additional examples of PointPatchMix for qualitative analysis in the lower right figure. The diversity of target values and patch ratios in the generated point clouds highlights the effectiveness of our proposed patch scoring module. By generating targets based on patch contents and emphasizing important regions during training, PointPatchMix enables the network to focus on informative areas, resulting in improved point cloud classification performance. In conclusion, data augmentation is a critical and challenging task in point cloud processing. To address this issue, we propose a novel mixing-based data augmentation method, PointPatchMix. This approach generates diverse training samples while preserving the local characteristics of point clouds. Our patch-level mixing strikes a balance between block-level and point-level mixing methods and outperforms their performance. Furthermore, our patch scoring module assigns more realistic content-based targets to the mixed point clouds. Experimental results demonstrate that PointPatchMix performs competitively in various settings, including real-world point cloud classification, synthetic point cloud classification, and few-shot learning settings. It also demonstrates strong generalization across multiple architectures and enhances the baseline model's robustness. Our study focuses primarily on point cloud classification, which is crucial in 3D scene understanding. However, point cloud data has various applications in other domains, such as scene and part segmentation. Thus, a promising future direction would be to broaden the scope of our investigation to encompass these areas. This effort could contribute to the development of more comprehensive and sophisticated point augmentation methods for point cloud analysis. That's all, thank you.